Hello, Professor Sargent here with you again. I stumbled across an interesting approach to finding the first n positive integers, what their sum is, and also summing up the squares of the first n positive integers. So here's our first part where we find the sum of the first n positive integers. This does not involve, at least not directly, any induction nor geometry. We're going to count something two ways. On the one hand, what if we just write out from 1 through n, all of those squared in what we're subtracting there, versus 2 squared through n plus 1 squared in what we are subtracting from. Now, please accept my apologies for some occasionally sloppy writing. It's been a while since I've used this tablet, number one. And number two, I am doing an experiment with turning these long-form horizontal videos into shorts. But imagine that we have like terms there lined up diagonally. We would have the 2 squared, the 3 squared, on up to the n minus 1 squared and the n squared, all canceling out when we subtract, so that we just have the quantity n plus 1 squared minus 1 squared. And when we multiply out the quantity n plus 1 squared and subtract the 1, we'll be left with n squared plus 2n. Now let's count that same thing another way. Since our indexing is the same, let's collect the difference of those two sums into the sum of the differences. Next, we will multiply out the quantity k plus 1 squared and combine like terms. And when we do so, we'll start to see something that looks like what we're looking for. We're looking for the sum of the first n positive integers. Instead of having a sum of sums of two terms, we can split that up into two different sums with the same indexing. And now it's looking even more what we're looking for, where we're looking for the sum of the first n positive integers. We can factor out a 2 from that first sum. Now we see exactly what we're looking for. And on that second one, if you add up n copies of 1, you're just going to have n. We've counted the same thing two different ways. And I'm circling what we had after simplification in each case. We're going to set those two things equal to each other. Once we've done that, we're going to immediately combine some like terms. Subtract n from both sides. factor out that n. On the right-hand side, that is in common to both terms. And divide both sides by 2. And now we have the sum of the first n positive integers, what that is equal to. Let's see if we can apply the same approach to finding the sum of the squares of the first n positive integers. Again, counting 2 ways. Although this does not rely on induction nor on any geometry, at least neither one of those directly, this will involve some recursion. However, if you look at the thumbnail for this video, I think I may have found a little bit of a way around that. All right, here we go. Writing down what it is that we're going to count 2 different ways this time. In this case, we'll have 2 cubed plus 3 cubed on up to n cubed and n plus 1 cubed. What we're subtracting, we'll have 1 cubed plus 2 cubed on up to plus n minus 1 cubed and n cubed. And we will, again, in that subtraction, combine like terms, and we're just going to be left with the quantity n plus 1 cubed minus 1. Multiplying out the quantity n plus 1 cubed. And subtracting that, subtract from that a 1. Now counting the same thing another way, as in the previous case, instead of having a difference of sums, we're going to have a sum of differences. And then we will multiply out the quantity k plus 1 cubed and combine like terms by subtracting a k cubed. Remember, here we're looking for what is the sum of the squares of the first n positive integers. And we're starting to see that now. We have the k cubes canceling out, and we do have involved in that sum a k squared. I'm going to split up that sum of 3 terms into 3 terms of sums. From those first two, factoring threes out, as before, we know that the summation of n copies of 1 will just be n. So 3 times the thing that we're looking for, sum of the squares of the first n positive integers. On that second, we're taking advantage of the formula that we just developed, and of course is known by other methods as well. Because what we began with at the top of each of these, quote, slides was the same thing. We've counted those 2 different ways. So what I am circling off here, we're going to set those 2 things equal. Be able to immediately subtract n from both sides to combine like terms. And although it may not be necessary, to make this a little easier to look at, I'm going to multiply both sides by 2, distributing. And when I first wrote this out, I'll admit that I did it on the left-hand side and then forgot to do it on the right-hand side, and so had to do some erasing to fix things up. You're going to see the corrected version. And I'm going to distribute the 3n to the quantity n plus 1 and follow that up by combining some like terms again. We'll be able to subtract 3m squared and 3n from both sides. On the right-hand side, I factored out the common factor of n. Going to do some more factoring, and then divide by 6 to isolate what it is we're looking for, which is the sum of the squares of those first n positive integers. Further factoring on the right-hand side, the quadratic that we have. And divide both sides by 6. Now we have the sum of the squares of the first n positive integers. And again, this approach did not involve any induction nor geometry, nothing that is directly used at least. It did involve some recursion by using the formula for the sum of the first n positive integers when we had the n times the quantity n plus 1 all over 2. So we did have some recursion, but check out the thumbnail. I think I found a little bit of a way around that again. Hopefully you found this interesting. That's all for now. Stay safe and healthy.